So I want to look at Surds. As I said, I'm going to look at Surds. Um, uh, what happened here? Something else. So, um, I'm going to look a little at Surds. Let's see what it's following to make it black. Yes. We're going to look, do a bit of review on indices, and then we look at logarithm. Oh, there's an M here, logarithm. Right? So I think we did some work on indices before, if you recall. Then we're going to look finally at logarithm. Right? So let's start with Surds. Right? What's a Surd really? What's a Surd? Let me give you some example. You see numbers like this. Square root of 2. Right? And there's an interesting story. Let me tell it quickly. Right? There is a story as to how these numbers came up, right? So there's a group of people that lived, well, they lived in ancient times. They were what we call it Pythagoreans, right? And the Pythagoreans basically, they were a sect of people like that. They had certain beliefs borrowed from, well, remember those times, you never used to have, a separation between people's religion and science and mathematics and all of that. No, right? You would find that these people, they have their religious beliefs, they subscribe to certain scientific beliefs, and among this group, well, of course, if they're called Pythagoreans or Pythagoreans, right? They believe the Pythagoras theorem, right? All of you know the Pythagoras theorem. Oh, God, this is supposed to be a right hand. The Pythagoras theorem. And the Pythagoras theorem basically says that if down here is A, down here is B, and down here is A squared plus B squared, right? And the square root of that, right? So, one of the guys among them, one of their believers, said that, you know what, if we have a triangle, a rectangle triangle, down here is 1 and down here is 1, then down here is going to be root 2. Right? So if you have a rectangle triangle and the two sides are 1, 1 each, then if the hypotenuse, according to Pythagoras theorem, will be root 2. The thing about square root of 2 is that this kind of number was not known until then. And the number line was already so full of numbers because, between, okay, let's say you have 1, 2, 3, minus 1, minus 3, minus, you know that between 0 and 1, there is an infinite set of numbers, infinite set of numbers between 0 and 1. As a matter of fact, between any two real numbers, there is an infinite set of numbers between any two real numbers, no matter how close. If you take the number 0 and you take the number 0.00001, there's an infinite number of numbers between here. Right? So they said, look, the number line is already full, so to speak. Now you are telling us there's a new set of numbers that gotta fit them. You gotta find place for them on the number line. So it didn't go down well with them. I've got to show it, story a little short. And so what they did, they decided, you know what, you can go and take a picnic on a nearby island. And they carried the guy, who came up with this idea, this Route 2 business, right? They carried him with it on the picnic. And guess what? When they came back from the picnic, he didn't come back with it. So whether they kill the man or bury him there, or whether they throw the man overboard, we don't know. But the man was never heard of again. Right? At least that's what the story says, right? I mean, these mathematics stories, you can hardly verify them, right? Because of lack of written history, you know. Everybody, all they did was record colonization and wars, and so people hardly took the time to write down mathematics history, right? Yeah, so that's how this idea of swords came about, right? And numbers like we got root 2, we got root 3, and all of that, right? So yeah, it's a funny story, but that's how the story goes.
Excuse me, sir. This
And yeah.
thing song in low. I could hardly hear you.
Oh, you can hardly hear me. I wonder if I have to turn up my volume. Are you hearing me better now?
A little better. You could turn up more if you want.
Okay. But I'm gonna try something now, right? Feel free to interrupt at any time and ask any questions, right? And let me know if you are hearing, right? I think I did a video once where I chopped out all the little bits I tell you in stories and experiences and so. Because I never know what you'll do with it later on. So I chopped all of it out. So it's good I start recording now. Whoever missed the class would miss the story. Right? You gotta come to the classroom. It's not a correspondence course, right? It's not a fully online course. It's just the one, two people who's missing will have a recording. Okay, good. Yeah, so as we said, we talked about some examples of swords there, right? So, you know, let me give you a couple of examples. Root 3, root 2, I mentioned, right? Root 4, you wouldn't call it a sword, right? Because that's a nice round number 2. But a sword basically falls into the category of irrational numbers, right? Because they can't be written as an exact fraction, where the numerator denominator can be integers, right? Root 3, you just can't write it as a fraction with the denominator and the numerator being integers, right? Yeah. And if you were to try to maybe put them in a calculator, root 3 is I think what you call a non-terminating decimal, right? You'll find that with it. Good. And then you'll hear, just to introduce some things you might hear about swords and so, right? You'll hear about what we call an entire sword, right? What's an entire sword? Root 2, you call it an entire sword, right? Sword. you'll have, let's say, 2√2, you call it a mix sword, you know. You have these names, and so some different textbooks would, they'll give you all kinds of things. So let's explore swords a little, right? For example, let's try to write swords in their simplest form, right? So writing swords in their simplest. So let's take an example. You have something like this, root 28. Root 28. So what you want to do with a number like this, right? You want to see if there's any perfect square that is a factor of that number. And then indeed there is, right? So you notice as 4 multiplied by 7 will give you 28, right? So what you can do, there's a rule that allows you to split this up. And I don't want to appeal to indices here, right? If you know a little bit of indices, you should. I know I'm going to indices afterwards. Right? Like this means 4 by 7 to the half power, right? And this can rightly be written as 4 to the half times 7 to the half, right? Same thing here, right? You can put square root of 4 and square root of 7. And you know that the square root of 4 is not a sword, it's a nice number like 2. So you end up with 2 root 7, right? So writing root 28 in its simplest form, you get 2 root 7. Get that? Look for a perfect square that is a factor of the number under the radical sign or the square root sign, right? Like, let me give you another example. Maybe. Who's trying to call me now? Let's take another one. So you have, all right, the square root of 63. Wonder why this force me is 16. Let me see if, you know, it's somewhat something important. Like this as root 9 by root 7. So you have what? 3 root 7, right? Get it? Of course you can do it. You can, well, I don't have to tell you that, well, you can take this and write this back, right? And see the process, right? You see the process of doing it the other way around. And I'll tell you what, it's good to know the process. The reason why both taking this and getting this, or taking this and getting that, right? You never know, and that's a funny thing, huh? It's how the entire and all your courses are taught. We try to teach you everything, right? I mean, we can't teach you everything, but we try to teach you a little bit of everything. And let me put it that way. Because we never know what you'll need later on. Right? That is it. And that is why I just want to deviate just a little to tell you. It is the reason why there is this group of people, right, who they were called post-modernist curriculum developers, right? And they're saying that, look, you see this thing where you're trying to teach children things and like no, I can't pick out a situation just like that where you will need to take this and get it in this form, right? I think in one of the worksheets there is a thing that you make use of this knowledge, right? So sometimes you want to know, why am I being taught all this thing, you know? Think about your bio courses, your chemistry courses, all those little bits, and as I told you before, you got a job, and 99% of what you were taught, you don't have to use, because the job doesn't require it. So there are these people who say, you know what? No. Why not let's teach by something called, there's some of them calling it project-based learning, right? Project-based learning, right? Some people say talk about problem-based, right? Problem-based learning, right? And what they're saying is, look, let students or yes, students find some a project, or they're given or they find a project, and that probably has to do with some problem that the community or the country or whatever is facing, right? Or it can be a project, it can be a problem, and let them try to solve it. And in the process of solving it, right? They might very well have to learn a little bit of mathematics, a little bit of science, a little bit of, all kinds of things, business, whatever areas they have to learn. But only that will help them to do this project, to carry out the project or solve the problem, right? So they see the need, they say, what, this thing is useful to do this project, or it's useful to solve this problem, right? Some people are arguing to go that way, you know. As a matter of fact, I had an idea I was trying to throw to my fellow colleagues in the division, right? And I'm borrowing that idea from, there's a doctor in Georgetown named Dr. Fox, right? I think she got an award for, I think she came up with a process that nobody in the whole wide world knew about it before, right? And I think it had to do with some process to break down crude oil using something. I can't remember. She got some award for it, right? As a best woman scientist in the world, or I don't know where, right? But she has a foundation where students would, they come to her with ideas. Not her, I think there's a whole group of them. And I was trying to bring that idea to Boston, where students would come to us with an idea, like the computer science boys would say, you know what, sir, I want to develop an app that will do this, or I want to develop a website that will do this, or the chemistry people say, you know what, I wanna, develop a process to do this. The bio people might say, you know what, I want to get into the conservation of something, or God knows what you'll come up with, right? Or you might say, look, I want to develop a processing method for some kind of food that we are wasting a lot. And good. And what happens is that you're going to study this particular problem, right? Like right now we get in blackouts in this whole country. You want to think, well, can I propose? Some people are only fine during my class to be calling me. And some students having trouble logging in and all that. Anyway, yeah. So you never know by the end of the 4 years, right? When you come out of here, you have something that can be a side hustle for you. It could also be a major business, right? It could be something that can generate some income for you. Or you never know you're going to it full time, right? You never know you're going in full time, right? And of course, the lecturers who mentor you and so might very well want equity in the business, So yes, sometimes you thought stuff that you want to know, what am I going to do here, right? And that idea would have gotten you to be using at least a small fraction of your knowledge meaningfully, right? Meaningfully. Let's get back to this, right? So let's talk a little about maybe addition and subtraction of Surds now. Go with addition and subtraction. Surds. Good. So just like in algebra, right? Where when you're dealing with, okay, 2x plus 3y plus let's go with 4x minus y. You can't add the x and the y, right? You have to add the x and the x. And if you subtract the y from the y, you can do that. Same thing with sort. If you have, let's say, okay, 2 root 3 plus 7 root 3, because they both have a common sort inside, right? You can add this and say, oh, you have 9 root 3. Right? But if you have, let's say, all right, 8 root 3 plus 5 root 2, you can't do nothing else. Right? Because they're different. The sort, there isn't a common sort base. Right? So this one here, using your distributive law, you could very well do this. You factorize out root 3 and you get 2 plus 7, which gives you your 9, right? But you don't write root 3 9. Don't write that. You put a 9 in front, right? Put a 9 in front. Because sometimes some people just draw this line very far and the 9 gets under the root from it, right? Think you getting that so far?
Please repeat
So
it, sir. Can you please go over, sir?
They must be. You want me to go that back?
Yes, sir.
Yeah.
Sir.
What we're saying here, is that you cannot add two swords that is different. Like you got root 3 there, and you got root 2 here. You can't add it.
Okay,
Right?
sir.
Just like you
Excuse me,
can't
sir.
add.
Can you please
Yeah.
start from the top? I was lost at the top part with the 2x plus 3y plus
Yeah.
4x minus y.
Yeah. So we are saying that you can't add x and y. You can't simplify it for them. Right? What you do, you usually add the x and the x, and that's how you get 6x. 3y minus y gives you 2y, right? So you can only add and subtract similar terms. The same goes for sword. You have 2 root 3 and you have 7 root 3. You have a similar sword. You have root 3 in both terms. So you simply add the two numbers. 7 and 2 give you 9. Right? On the other hand, look at this one. Right? Root 3 plus 5 root 2. You just can't add these because this is root 2 and that's root 3. Right? So you just can't add it. You gotta leave it just like that.
Excuse me, sir.
Yeah.
So for this one with root 3 and root 2, you're just putting back the answer just like that.
Well, I wouldn't ask you something like that. I may not ask you something like that.
You know, sometimes you might ask, but anyways, all right.
Yeah, you're right. If you come across a question like that, you would know that yes, you can simplify that for.
So the answer will remain the same.
Yeah.
Okay, no problem.
Of course, somebody can tell you to evaluate that, write it as a decimal. So you have to punch all of that in the calculation, add them up, right? Because root 3 is a number, plus 5 root 2 is another decimal number. And you can add them up and maybe give your answer. That's if they ask you for that. Right? If they ask you for that. If they don't, well, you can't do anything. Right? If they just say simplify this sort, you gotta know that this sort just can't be simplified anymore. Get it? What you call they must share a like sword in each term, right? So sometimes though, right? Sometimes you might have two swords that they don't look alike, They look like you can't add them and so, but sometimes you can very well add them. To give you an example, you can have something like this. Root 12 minus root 24. Maybe you have to, somebody tell you to simplify, simplify. So you look at it, you say, no way. Surds tells us that, if these two things are different, you can't just subtract them, right? But what you could do is see if you can break down 12 and you can break down 24. See if the two surds can actually have a common surd inside, right? So like 12, okay, it is 4 by 3, all right, I know. What's this one? 9 by 3. So it seems to be heading somewhere. You'll get 2 root 3 minus 3 root 3. And yes, we have a common surd there, right? So we can know 2 minus 3 will give you minus 1 root 3. See? So you could simplify it. So don't conclude or say, watch it. Oh, they're different. We can't subtract them. No, don't say that. See if you can simplify it. It may work. It may not work. But you just have to, you may just have to see if you can simplify it. Right? I lost my point. Good. Go to multiplication. Multiplication. Surds. Right? And like again, if you have x by y, you can multiply them, right? Regardless, whether it's different, you still can multiply. The same is true of surds, right? Like you get root 2 by root 2, you can multiply them, right? You get root 2 by 2, which is equal to root 4, which is 2, right? And then root 5 by root 5 is the same as root 5 or 5 times 5, which is root 25 equals 5. You can multiply it, right? Much like when you were dealing with and subtracting algebraic terms and expressions, when you were multiplying and dividing, and so very simple.
Excuse
very
me,
simple.
sir.
Yeah.
All right, you see, like when you put the 5 by 5 equal to 25, and you put back the 5, you don't put in back the root thing, you just put in 5 alone as the answer.
Well, square root of 25 is 5.
Mm-hmm. All right, good.
And if I'm to use, okay, I think these examples didn't really follow what I was saying here. If you have, let's say, root 2 by root 3, you can have that equal to 2 by 3, which is root 6. Right? So if they're different, that's no problem too. Right? In this case, both of them were similar. But in this case, they're different. You have root 2, you have root 3. Yes, you can multiply it. Right? You have root 2 by 3, which is root 6. Think you follow that? Huh?
Yes, sir.
Yeah. If you have, let me give you another example. One second. You have 2 root 5 multiplied by 3 root, let's say 7. Right? So you can actually multiply this and have what? You can have 2 by 3 is 6. And in the radical sign, you have 5 by 7, right? 5 by 7, you get 6 root 35. You can have that. Because 35 don't have there isn't a square number that can be a factor of 35, right? I don't think so. So even though the number here is different, You have 5 there and 7. You can multiply. You couldn't add them because they're different, but you can multiply them even though they're different. Like you have here, x by y, you can multiply x by y. You can add x and y. I mean, no, you can't add it, you can simplify it further. If you have x plus y, that remains x plus y. You can't go down more. But x multiplied by y is x1. Right? Same with soil. You couldn't add them, but you can multiply them. You want that, it's not so plain like this, right? Maybe it's a little more complicated. Go back to, let's say you have some of this, all right? Root 8 multiplied by root 10. So, what can you do with that? So let's say, all right, you have what? That would be root 80, right? And you can now see if you can simplify that, right? And you can see, I want to think that that is equal to 16 by 5, right? It's just, so yeah, 80, yeah. Right? And this here is a perfect square, so that will be root 16 by root 5, which will turn out to be 4 root 5. Let's take a final example on multiplication. Tell me if I'm going too fast or what, So let's see. Okay. Yeah, this is an easy thing, I would think, right? So you have something like this, right? So you get what? 2 times 3 is 6, and you get root 3 by 2, so you get 6 root 6, right? Okay. Ugly as it is, well, that's what you get. What you do? Can't do nothing more. Try another one. Uh, 2 root 12 by 3 root 8, right? So you get what? That's 6 root 12 by 8. You get what? 6. 6. Oh, my table. Table is in your finger. Yeah, right? Which is also equal to it's 16 by 6, right? This is 36. Yeah. This now, this part here, let me go up here. You get 6 root 16 by root 6. This is going to be 4, right? So 6 by 4 by root 6, right? So you get 24 root 6. Let's get something a little hard. Something hard. Let's go with something. Root 5 bracket root 6 plus root 7. After maybe simplify. Oh my, simplify. Right, something like this. Right, so you use your simple what do you call the thing? Distributive law, right? And you simply multiply this by everything in here, right? So you'll get root 5 by root 6 plus root 5 by root 7, right? And you'll get what? I don't think you can simplify this for minor plus, no? Root 35. I don't think that there are any factors or solitaire 35 that's a perfect square. So you might have to just leave that the way it is, right? I'm hoping that, well, maybe in another one, this wasn't well thought. Maybe that this you could have simplified a little more, and that you could have simplified a little more, you know? Yeah, maybe you'll see one like that someday. Well, we go again. A good one to know. Like if you have, let me show you this one. Root 8 plus root 3 times root 8 minus root 3. Anybody can think what that will turn out to be? Just finish quadratics, right? Yes, the man.
Yeah, sorry, it will be root 68. I mean 64. Root 64. 8 for root 26. And
Can you
yeah,
recognize this to be a plus b multiplied by a minus b, which is a square minus b square, right? I'll just do quadratics, you know. You gotta watch it and watch it good. So basically, it's going to be what? 8 minus 3, which is 5. Is that right?
I didn't thought about doing it like this.
Yeah.
Like I'm just so used to when I see like it's just expanding it. I didn't thought about.
Yeah,
like,
yeah. So that's the thing, right? Sometimes you the first thing that comes to your mind is use the brute force and ignorance, you know, that we have, you know, work the thing out and multiply everything out and so. But if you know, if you can remember like these things and say, okay, you know what, this thing has some resemblance to something I saw before, you know, and that's where you working in the area, you become familiar with these things and so, right? Good. We talked about then what? Surds, addition, subtraction. We talked about multiplication. We didn't mention division yet, right? Division, right? So let's see. Instead of division, you're going to see a lot. You're going to see the term rationalizing, rationalizing the denominator, right? You see that, right? Rationalizing. What are they talking about here? Let's take an example. Let's take an example. Say somebody tell you to rationalize the denominator of 3 over 2 root 6. Oh, something like that. What they're really telling you is that, okay, they don't want this rational number, this irrational number in the denominator. They want to get it out of here, right? They want to get it out of here. So And for those who are into the computer science boys should be able to comment here. If they were to program a calculator to do something like this, it is better if the square root is in the numerator. Right? I've heard that from programmers saying that the code is simpler to write if this here is in the numerator. So what you do, you want to rationalize. You don't want the denominator to have a square root inside. Any square root must be dealt with in the numerator. Right? Especially the older calculators and so, it's harder to do something like this. It's harder to do something like this. But if you find a square root of something and then the answer you get, then you divide by maybe 2 multiplied by 3. That's easier. But to put in a square root sign in the denominator of a fraction is very, very difficult. Right? I know we have come so far forward that is not the case now. You can write stuff the way it is, and the calculator is going to do it. Right? Maybe you can try it as we're doing the problem. Anyway, what we mean now is we have to get this radical sign out of the denominator. So there is a technique where you multiply the numerator and the denominator by root 7. Right? And what would happen? Well, it's like you multiply by 1 here, right? Root 7 over root 7 is 1. So you end up with 3 root 7. And root 7 by root 7 becomes 7. And that 2 becomes 14. And there you have it. You got 3 root 7 over 14 is the same as 3 over 2 root 7. Same girl, but just arrange it here and make up and, whatever else differently. And for those of you who are, well, I don't think any of you are old enough to know that in long ago calculator, this was a hard thing to put in. This was a hard thing. Right? But long ago calculator, what you do, you find the square root of 7, you press equal, it's going to give you a horrible decimal. You take that decimal, multiply by 3, and until you get, you press equal again, and then you divide by 4. Right? But as I said, to do this with a long ago calculator is very difficult. You take 3 divided by, right, 2 times root 7, and this root 7 wasn't easy to insert because you never used to put in root 7. You used to press 7 and then the square root, and then you have to remember you have to put a bracket here, right? You have to put a bracket and so, and that just creates a lot of problems with students, right? So it didn't lend itself to the kind of calculators that you had in those times, right? So this here was nice. You could see this in a calculator very easy. Let's do maybe a harder one. Do a harder one that involves see if I can find one that is a little. What's this one? And my intention here is not to exhaust all the possibilities, right? In your tutorial, we're going to do a lot more. Look at this one. You have 3 minus root 5 over 1 plus 3 root 5. So you have to rationalize that denominator. So this is what you do. You make use of that same thing that we had, that a plus b times a minus b is equal to a squared minus b, right? So we're going to do that here. We're going to multiply the denominator by what we call the conjugate of 1 plus 3 root 5. So you get 1 minus 3 root 5 over 1 minus 3 root 5. And what will happen? When you multiply the numerator, you'll have something ugly, but when you multiply the denominator here, right, this is what you'll get. Move it up a little bit. Just for some space, right? So you'll get this. And you'll do the multiplication, right? I'll skip that out. I'll multiply this by this. You know how to do that, right? It's like you're buying two binomials you're multiplying. I'll skip that. And you'll get something on top here, right? Skip that out. But at the bottom here, you're going to have 1 square minus 3 root 5 squared, right? Which will work out to be, and you will work out the numerator. But at the bottom here, you will end up with 1 minus 3 root 5 squared give you 9 by right? That's correct, right? So you will go over here. So you will end up with something over, what will it be?
Right.
45, so 1 minus 45, right? U minus 44. Anybody work out what the numerator will be? I just want to interject there to actually work out the numerator, right? So basically what you're having is this. You're going to have 3 minus root 5 times 1 minus 3 root 5 all over 1 plus 3 root 5 times 1 minus 3 root 5, right? Good. So if you were to multiply 3 by 1, you get 3. 3 by 3 root 5 will give you 9 root 5. Then you will multiply this minus root 5 by that one, you get minus root 5. And then minus root 5 by minus 3 root 5, you will have positive 3 root 5 squared. All over. I'll show you how this here, again, you saw this is applied here, right? Let's multiply. 1 by 1, you get 1. 1 by minus 3 root 5, you get minus 3 root 5. This by this will give you what? 3 root 5 by positive 1, you have positive 3 root 5. And 3 root 5 by minus 3 root 5, you get minus 9 root 5 squared. Right? So let's see on top here what happens. You get this will become 3, this part will become minus 10 root 5. This will become what? 5, right? 5 by 3 is 15 plus 15 all over. Down here, you notice that this part is going to become 0. This is going to become 45 because 5 root 5 squared is 5. 9 by 5 is 45. So 1 minus 45 will give you minus 44. So this now, 15 and 3 is 18. 18 minus 10 root 5 all over minus 44, right? So this can be simplified further. If you watch it good, you can actually divide is two a factorial if you divide everything by 2. So let me take everything this way. So we have 9 minus 5 root 5 over minus 22. Right? So you can do several things with it. You can rearrange this if you want. If we take out a minus sign here, you don't have to do this, but I'm just doing it. Take out a minus sign. So you get minus minus 9 plus 5 root 5. So this can be written as, okay, this can be written as 5 root 5 minus 9, and there is a minus sign outside, minus all 22, and this minus sign, and that minus sign will go. And you're going to be left with 5 root 5 minus 9 over 22. You don't have to do all of that. You could stop right here. Stop right here. Complicated?
Very much so.
But follow the procedure like you will multiply 2 by no, right? This 3
Right.
by everything in there, and then this minus 5 by everything in there. And you got all of it. Right? You get all of it. Right? The denominator, you see why the people said, you don't have to do the long multiplication. You can make use of this thing here. Right? And you could watch the denominator because it's 1 plus 3 root 5. And down here as 1 minus 3 root 5. That's a difference of squares. You can right away write 1, you have to put in this middle term. 1 minus 9 root 5 squared. Right? That's what it is. You could jump that step. You don't have to put in all of this in. Anybody's writing anything? I can erase, right? Not 10 root 5 over minus 44. So what we could do, take out, what's a common factor here? Okay, if I take this over down here, 3 root, thankfully. But laws of indices, lecture and your tutorial tutor is going to spend some more time on this. Give me a second, I just want to learn these people about something. Laws of indices. I think you have done. Do you want to take a pause here? Y'all want to pause here a little? Or let's go through. I don't want to cover logarithms this evening. I'll just go through laws of indices and give it a rest because it's too much for you already. You want us to go through indices?
I already get to know.
So you want a break or you want us to go through indices and finish early?
Break, sir.
You want a break? All right. So
Yes, sir. To
now
recuperate
is
and come back fresh again.
all right. So let's say now it's 6:40. Come back at 7, and we'll take a 10 minutes or 15 minutes on indices and finish. Right?
Okay,
Leave
sir.
logarithm the next day. Okay. Oh, just reviewing the record. Yeah, so as I was saying, we're going to do a brief overview of laws of indices. Because I think by now you're, with all that sort of business, your brain probably is clogged up. So we're going to just do an overview of the laws of indices. And the next time we meet, we're going to do some examples, some more on indices, culminating in equations where unknown is in the index, right? And that will lead us straight into logarithms, right? So that'll be a nice chunk of stuff that we'll do. That's next month. No, that's next Tuesday, right? Yeah. This class and another class I'm doing for IDC is very similar. So I don't know if I get confused with the day. Pictures of this at your CXC level, you know. Let me use, okay. You have p to the x plus, times p to the y, you know that's p to the x plus y. You have p to the x divided by p to the y is equal to p to the x minus y. I guess you know all of this, right? P to the x raised to the y power is the same as p to the xy power, right? I think there's another one like this, the square root of p to the x, or not square root, let's say the y root of p to the x is equal to p to the x over y. I think you all should know these rules from CXC, right? There's a, it's not a new rule, it's really what we call a corollary. You know, it came from the other rules that p to the 0 is equals to 1, right? And if p is a non-zero number, right? That is. And I think there's another one, 1 over p to the x is the same as p to the minus x, right? These are, they're not new rules. These two here, they're not new rules. They came from these over here, right? They came from these over there. But, so that little, you know, review of indices, I'm going to do examples, and so there are going to be plenty in the tutorial for you to refresh your, yeah. Okay, so as I said, right, we're not going to do too many examples of these. Well, we're not going to do any, in fact, this evening. I want you to be fresh with this the next day when we come, right? So keep this in mind, these basic rules, right? And when we meet back on Tuesday, I'm going to elaborate on each of the rules using examples, right? Then we're going to do some equations that involve the unknown being in the index, right, or in the power. And we'll see the limitation of these basic rules. I didn't hear that.
Don't know what could bust your face.
All right, all right.
Young girl think to go up, sir? Young
Okay, yeah.
Being impress your
Yeah, so we are going to finish up this the next time we meet, and then we lead straight into logarithm, right? So we'll close it. We'll close it.